Welcome to our continuing series of lectures on fundamentals of transport processes. We were going through transport in one direction, transport of mass, momentum or energy in one direction. We had looked at mass and heat transfer from a flat surface using a Cartesian coordinate system. That was the simplest coordinate system that we can consider, because the three axes are straight, independent of position, and the planes of constant coordinate are all perpendicular to each other. We had also progressed to a cylindrical coordinate system, where the surfaces of constant coordinate were cylindrical surfaces. So, this coordinate system was defined by one coordinate was the distance from the axis of the cylinder, the radial distance from the axis, and the other was the distance along the axis, the axial distance. And we had solved a heat transfer problem in that cylindrical coordinate system using separation of variables. We had also solved a heat transfer problem using the similarity solution. If you recall, we had solved the problem of heat conduction from a wire using a similarity solution. That had the distinguishing feature that the temperature there was going to the temperature in that case was going to infinity at the wire itself, but despite that we were able to get an analytical solution using the similarity transform, in this case of a heat conduction from a wire. And then we had gone on to momentum transfer problems. As I said, in momentum transfer there is one additional factor, which is the pressure gradient, which is not in general present in heat and mass transfer problems. And last lecture we had looked at the flow in a pipe, a cylindrical coordinate system in which the surfaces are surfaces of constant distance from the axis of the pipe. And in this case we were considering a fully developed flow, the assumption being that there is no variation of the velocity along the streamwise or the axial direction. The velocity is the same at every downstream location. That is a fully developed flow. And we had written a momentum balance equation for that particular situation, where there could be variations in time, but there was no variation in the axial direction. For the x momentum, the axial momentum, the momentum along the axis of the pipe. And we had chosen surfaces at z and z plus delta z, written down a balance, and finally we had got this balance equation. The new feature here was the pressure. The pressure between the ends of the pipe is different. That is what is driving the flow, the pressure difference between the two ends of the pipe. Therefore, whenever we consider a surface, whenever we consider any surface, there is an additional pressure that is exerted on that surface. Pressure is always compressive. It acts along the inward unit normal to the surface. So, for the differential volume that we are considering the momentum balance in the x direction, in the streamwise direction. The pressure is in that direction only at the two annular faces at x and x plus delta x. Therefore, that pressure has to come in at these two annular surfaces, in addition to the shear stress, the momentum transfer across the cylindrical surfaces. As I had explained in the last lecture, the shear stresses are parallel to the surface, the pressure is perpendicular to the surface and compressive. So, in this x momentum balance equation, the pressure at the surfaces at x and x plus delta x does contribute to the net force on this volume. The shear stress at the surfaces at r and r plus delta r does contribute to the net force. The pressure at these surfaces does not, because the pressure at these surfaces is in the radial direction. So, on that basis of momentum balance, we had got this momentum conservation equation for the unsteady flow. And if you recall, in the last lecture we had solved it for the special case of a steady flow. So, we had considered that there is no time variation, we considered a steady fully developed flow, and we solved for the velocity profile of that steady fully developed flow. with the boundary condition that at the surface of this pipe the velocity has to be equal to 0, the no slip condition. Basically that at a solid surface the fluid velocity is equal to the velocity of the surface itself. In this particular case the pipe wall is not moving and therefore the velocity is 0 at this surface. Based upon that we had solved this equation and got an equation for the velocity profile, and from that for the shear stress at the wall, okay, all based upon this pressure gradient. Okay, all based upon this pressure gradient. We had got the maximum velocity, the mean velocity in terms of the pressure gradient. Okay. If you recall, the mean velocity was equal to the integral, the flow rate, okay, the integral of the velocity over the cross section. And while doing that calculation, one has to be careful. Okay, the flow rate itself is equal to 2 pi integral 0 to r dr, okay, times ux at the location r. Okay. That is because the area element in a cylindrical coordinate system, okay, the area element in a cylindrical coordinate system is 2 pi r times dr. Okay. The perimeter at any location r is 2 pi r and the thickness of that interval is dr. So, the area element is 2 pi r dr, okay, in the cylindrical coordinate system, and that is one thing that one has to be careful about while doing this calculation. In any case, once you do this calculation, you will get the flow rate, divide that by the cross sectional area and you get the average velocity. And as I had shown you in the last lecture, the average velocity is equal to 1/2 of the maximum velocity for a pipe flow. Okay. And the friction factor is defined as the wall shear stress scaled by the inertial scales. Okay. The friction factor is defined as the wall shear stress scaled by the inertial scales. And from this we had got an expression for the friction factor as a function of Reynolds number as well. And we found out that the friction factor is equal to 16 by the Reynolds number, okay, where the Reynolds number could be defined either in terms of the pipe diameter and the average velocity, or the pipe radius and the maximum velocity. These two are the same in this case, okay, whether you define it in terms of the pipe radius and the mean velocity, or the pipe diameter, pipe radius and the maximum velocity, or the pipe diameter and the mean velocity. This is not true in general. For example, in a plane channel this will not be true, but for the particular case of a laminar flow in a pipe this is true. Okay. So, this was the log, it is called the Moody plot. Log of friction factor versus log of Reynolds number. On a log-log graph the slope is -1. Okay. If f is equal to 16 by Re, log f versus log Re will have a slope of -1. Okay. And at a Reynolds number of about 2100 a transition takes place. You no longer, this law is no longer satisfied. Okay. This law is no longer satisfied, and there is a transition to some other velocity profile in which the friction factor is much higher than what it would have been for a laminar flow. Okay. For a laminar flow, if I had extended this line of slope -1, the friction factor that I would have got is much lower than the friction factor that is actually observed in experiments. Okay. And the friction factor in experiments is dependent in general on the roughness at the wall of the pipe. You have a lower value for a smooth wall, and as the wall roughness increases you get a higher and higher value, okay, depending upon the roughness. Okay. Those are characteristics of what is called a turbulent flow. Okay. So, in this lecture I will try to give you some physical insight into what happens in turbulence. It will not be as quantitative as we were able to do for a laminar flow, because turbulence is a complicated phenomenon, not completely understood yet. Okay. Okay. At low Reynolds number, as I had just shown you, up to a Reynolds number of about 2100, you have a parabolic velocity profile. Okay. And at a Reynolds number of about 2100, there undergoes a transition to a different kind of profile. Okay. That is flatter at the center and steeper at the walls in comparison to a parabolic profile. Okay. A parabolic profile will look something like this. This profile is flatter at the center and steeper at the walls. Okay. So, this is what is called a turbulent flow. And this is what is called a laminar flow. And turbulent flows typically for Reynolds number greater than 2100. Okay. However, if you do take care to maintain to reduce the level of fluctuations in the flow, you can maintain the flow in a laminar state even at a higher Reynolds number. Okay. So, even when the Reynolds number exceeds 2100, the laminar velocity profile is still a valid solution of the momentum balance equation. Okay. Even when the velocity exceeds 2100, the laminar profile is still a valid solution of the momentum balance equation. The problem is that it is not a stable solution. Okay. And any small disturbance in the flow will spontaneously make it go to a turbulent state. Okay. If you were to describe it simplistically, okay, one could say in one dimension, for example, the transition to turbulence looks something like this. Okay. If I have an object at the minimum of a potential well, say, okay, and there is a force downwards, okay, if I do displace this object a little bit, okay, it is at an equilibrium state at the minimum point, it is at an equilibrium state, all forces are balanced. If I do displace it a little bit, the force tends to return it back to its original location. Okay. So, that is a stable steady state. Okay. On the other hand, if I had an object on, okay, a hill rather than a valley, okay, this location here is a steady state. When the object is kept at the maximum of that hill, this location is a steady state. The forces are balanced in this configuration. Okay. So, that is a steady solution. The problem is that if I displace it a little bit in either direction, the forces tend to take it further away from this steady state. Okay. So, in that sense, this is an unstable steady state. Okay. And any small disturbance will tend to make the system go away from that steady state. Okay. So, the laminar flow is the steady state. Okay. Okay. I have shown it schematically only in one dimension. Similar, the flow is more complicated, the velocity is defined at each point within the flow and so on. Okay. But simplistically, this is the picture. Okay. And like a configuration like this is called a configuration of neutral stability, because if you displace it a little bit, it does not come back, it does not go away. Okay. So, that is the transition. Okay. So, this is the transition, simplistically put. Okay. This picture, I should warn you, does not apply for the laminar to turbulent transition in a pipe flow. Okay. It applies for other kinds of stability problems. Okay. You often see this kind of a picture drawn. It applies for other kinds of stability problems. It turns out that the landscape is much more complicated. Okay. For the laminar to turbulent transition, the landscape is actually much more complicated. What it actually looks like is something like this. Okay. What it actually looks like is something like this. What that implies is that it is stable for infinitesimal displacements. If I displace it only by a small amount, it will still be stable. If I displace it by a large amount, it will go to some other state. Okay. That is the situation for pipe flows. Okay. So, if you maintain the disturbance level below a certain value, it will come back to the laminar state, but however, when it goes beyond a certain value, it will go to a turbulent state. Okay. So, therefore, one could in principle maintain the flow in the laminar state by completely damping out disturbances, but in practical applications there are always disturbances in nature, okay, and those disturbances will spontaneously make the system go to a turbulent state. And in most cases that transition takes place at a Reynolds number of about 2100 for reasons I should note that are not yet completely understood, but once the disturbance takes it to a turbulent state, you get to something that is a universal velocity profile, average velocity profile, independent of the disturbance that took you to the state. Now, the turbulent velocity profile is not a steady velocity profile. Okay. The laminar velocity profile is a steady velocity profile. So, if I look at some particular point and I ask what is the fluid mean velocity, okay, that fluid mean velocity is only in the x direction. Okay. That fluid mean velocity is only in the x direction. Okay. So, I have the x direction here and I have the r direction here. That fluid mean velocity is only in the x direction and it is independent of time. Okay. So, for the laminar flow, okay, if I plot the velocity at any location u x, okay, as a function of time at one particular location, say, it has a steady value, okay, and u y and u z, I am sorry, this is a radial coordinate system, okay, and u r, the velocity perpendicular to the axial coordinate, this will be equal to 0. Okay. On the other hand, in a turbulent flow, okay, there is an average velocity at any location. Okay. There is an average velocity at any location. Okay. However, if you take the instantaneous velocity, it is fluctuating about this average value. Okay. It is fluctuating about this average value. Okay, and it is never equal to a constant. Similarly, in the cross stream directions as well, if I plot the velocity at any location, these velocities are also fluctuating. Okay. On average they are 0, but they are fluctuating about 0, and as a function of time, right, you do get a fluctuation in the velocity profile. Okay. Now, this fluctuation in the velocity profile is because of the presence of what are called turbulent eddies. Okay. These are velocity fluctuations within the fluid. Okay. Basically, an eddy is a parcel of fluid that is in correlated motion. Okay. These eddies have different sizes all the way from the large scale. Large scale is comparable to the pipe diameter all the way to very small eddies. Okay. And the transport of mass, momentum and energy takes place due to these turbulent eddies rather than due to the diffusion due to the molecular velocity fluctuations. Okay. So, primarily the transport takes place due to turbulence, due to the turbulent eddies, the transport of mass, momentum and energy due to the turbulent velocity fluctuations, and not due to the molecular velocity fluctuations. For this reason, the rate of transport in a turbulent flow is much higher than it is in a laminar flow. Okay. If you recall, when we did the kinetic theory for gases, I had shown you that all of these diffusion coefficients, okay, the diffusion mass diffusivity, the thermal diffusivity and the momentum diffusivity, all of these scale as the mean free path times the root mean square fluctuating velocity of the molecules. Okay. They all have dimensions of length square per time. This is due to molecular diffusion. Okay. This is due to molecular diffusion. We had estimated these diffusion coefficients. The mean free path is of the order of 0.5 to 0.05 micrometers. Okay. So, approximately 10 power minus 7 to 10 power minus 8 meters is the mean free path, and the VRMS is of the order of 300 meters per second, okay, in gases. In liquids, the diffusivity depends upon the mechanism of transport. In a turbulent flow, at the simplest level, one could also define the turbulent diffusivities. Okay. One could also define at a simplest level turbulent diffusivities. These will scale as the fluctuating turbulent velocity, the turbulence fluctuations, the velocity of the turbulent fluctuations times a length scale for the turbulence. And that length scale for the turbulence is what is called the eddy size, the eddy length scale. So, you have a length scale for the eddies, a distance over which there is correlated motion. This correlated motion is what is transferring mass, momentum or energy. Therefore, you have a length scale for the turbulent eddies and you have a velocity for these turbulent eddies. And at a simplistic level, this product is what would give you the turbulent diffusivity. Now, in most cases, the largest scales of turbulence, the largest eddies that I had told you are comparable to the system size. The largest eddies are comparable to the system size, and the largest velocity fluctuations are comparable to the mean velocity. The velocity fluctuations in the streamwise direction in a turbulent flow are typically about 40% of the mean velocity. So, this will typically scale as a large scale times the mean velocity, slightly smaller, a factor of 10 or so smaller, because the largest eddies are not exactly of the same velocity as the fluid mean velocity, but it would scale similarly. And you can see that in this case, for typical application, R would be about a centimeter to a meter. And the fluid mean velocities would once again be similar in magnitude. They would be of the order of 10 power minus 2 to about 1 meter per second. So, the mean velocity is much smaller than the RMS velocity. The average eddy size is much larger than the molecular mean free path. However, this product is usually much larger than the molecular diffusion coefficients. This product, you can see the product will vary from about 10 power minus 4 to about 1, whereas this the molecular diffusion coefficients are 10 power minus 5 in gases and even less in liquids. So, for this reason, the turbulent diffusion coefficients are much larger than the molecular diffusion coefficients. I should caution that this picture is not exact. When we calculated the molecular diffusion coefficients, I had told you the basic assumption when we did the gradient expansion for the concentration about the location z is equal to 0, we had expanded it in a series. That expansion can be truncated at the first term only if the molecular scales are much smaller than the system size. In the case of a turbulent flow, the largest eddies are comparable to the system size, and therefore, that expansion is not exact. You cannot neglect the higher order terms, strictly speaking, because the ratio of the largest eddy size to the system size is not a small number. But still, this serves as a useful analogy to understand why turbulent diffusivities are much larger than molecular diffusivities. And this also explains why near the center of the pipe, the velocity profile is much flatter. The velocity profile near the center of the pipe is much flatter because the turbulent diffusivities are much faster. Momentum is transferred due to the turbulent fluctuations, and this is a much faster process. So, that tends to equalize momentum much quicker along the center of the pipe. So, the center of the pipe, because cross stream fluctuations are equalizing momentum much faster, the velocity is approximately a constant. It is more plug like in comparison to a laminar flow. Near the wall of the pipe, the flow, the velocity is much steeper. And it is because of this fast transfer of momentum from the center to the walls, momentum transport rates are much higher. Therefore, the shear stress is much higher, because the shear stress is just the rate of transport of momentum per unit area per unit time. The shear stresses are much higher, and therefore, the friction factor is much higher than what you would have for a laminar flow, because these eddies transport momentum much faster across the pipe, and for that reason the friction factor is much higher than what you would expect for a laminar flow. Similarly, the other transport rates, the transport of mass and energy in a turbulent flow, are also much higher by orders of magnitude in comparison to a turbulent flow, in comparison to a laminar flow, okay, as shown by the orders of magnitude difference in these diffusivities. Okay. In these diffusivities. Okay. So, near the center it is almost flat, close to the wall, okay, close to the wall, okay, if you look close to the wall of the pipe, okay, you do have a region where the flow is laminar. Okay. There is a region close to the wall of the pipe, okay, where the flow is laminar. Okay. It is called the viscous sublayer. Okay. How do we get the thickness of the viscous sublayer? Okay. The Reynolds number is large. Okay. So, as far as the flow near the viscous sublayer is concerned, the radius of the pipe is actually not a relevant length scale. The radius of the pipe is not a relevant length scale, okay, because the radius of the pipe is much larger than this viscous sublayer length scale. Okay. Across this viscous sublayer, the wall shear stress, the shear stress is approximately a constant. Okay. Now, if I were to plot the shear stress across the pipe, okay, we had an expression for the shear stress here. Okay. This was the expression for the shear stress. It is a linear function. Okay. It is a linear function. At r is equal to 0, the shear stress is equal to 0, and as r increases, the shear stress increases. Okay. So, the shear stress increases linearly as a function of the radius. Okay. This is if I plot as a function of the radius r, if I plot the shear stress tau xr. Okay. The shear stress increases linearly. Okay. So, if I plot as a function of r this shear stress tau xr, okay, this increases linearly, okay, as a function of r. Okay. However, if you are very close to the wall of the pipe, okay, if you are very close to the wall of the pipe, this looks as approximately a constant. Okay. The variation is small because the variation is equal to the slope times the length. Okay. So, if you are very close to the wall of the pipe, this variation is small. Okay. And within this region, we can approximately consider the shear stress as equal to the wall shear stress, okay, which we had seen earlier was equal to dP by dx times r. Let me just see the constants there. Okay. It's dP by dx times r by 2, okay, at the wall of the pipe. So, we can consider the shear stress to be approximately a constant. Okay. So, we would write, strictly speaking, the length scale in terms of the shear stress close to the wall of the pipe. Okay. Instead, the length scale is usually written on the basis of a velocity scale that is derived from this shear stress, okay, a velocity scale that is derived from this shear stress. Okay. It is called the friction velocity, okay, and it is defined as rho u star square is equal to tau w. Okay. This defines the friction velocity u star. Okay. You can easily see that by dimensional analysis, the density times a velocity square has the same dimensions as shear stress. Shear stress is a constant in this viscous wall layer, okay, and therefore, I can define a velocity scale as u star. The friction velocity is equal to root of tau w by rho. Okay. It is called the friction velocity. Because it is derived from the shear stress at the wall. Okay. Now, in the viscous sublayer, the only parameter that is fixed is the shear stress across this viscous sublayer, okay, and since the flow is viscous in this sublayer, okay, the turbulence effects are not important within this region close to the wall. Okay. I can define a length scale as nu by u star, where nu is the kinematic viscosity, okay, because we know that in the center of the flow turbulent diffusion is much faster than molecular diffusion. So, the kinematic viscosity is not really important near the center of the flow. Okay. It is only when you come close to the wall that the flow becomes viscous, when the length becomes much smaller than the pipe radius. Okay. So, any Reynolds number I define based upon this length from the wall will be much smaller than the macroscopic Reynolds number. So, there will come some stage as I approach the wall where viscous effects become important. Within this region, what matters is only the wall shear stress and the kinematic viscosity, and from that I can get only one length scale. Okay. And the distance from the wall, okay, is often written by the symbol y, scaled by this length scale. Okay. Okay. It is usually written in wall units, okay, y u star by nu. Okay. Is the relevant length scale as far as the viscous sublayer is concerned. Okay. And the velocity, okay, ux, okay, plus, okay, is usually written as ux by u star. Okay. The velocity is scaled by the friction velocity, and the length scale is scaled by this length scale obtained from the friction velocity and the kinematic viscosity. And this comes out of the assumption that the shear stress is approximately a constant across this region. Okay. So, that I can get only one dimensional parameter, the shear stress, or alternatively the friction velocity. Okay. Now, close to the wall, you know that the wall shear stress has got to be equal to mu times dux by dy. Okay. If the flow is purely viscous close to the wall. Okay. If the flow is viscous close to the wall, then the wall shear stress, there is no turbulent fluctuations because they get damped out by the time they come close to the wall. The wall shear stress is equal to just mu times dux by dy. Okay. Tau w by rho is equal to the kinematic viscosity times dux by dy close to the wall. Okay. And this is equal to v star square, okay, where u star is the friction velocity. I told you that tau w by rho was equal to u star square. Okay. Now, just rewrite this, okay, in terms of u by u star and y u star by nu. Okay. And you can easily see that dux plus by dy plus just has to be equal to 1. Okay. Because when I divide this, I will get d of ux by u star, okay, divided by d of y u star by nu. Okay. I divide throughout by u star square, this becomes equal to 1. Okay. So, close to the wall, I have the velocity profile ux plus is equal to y plus a constant, of course, but that constant is 0 because at y plus is equal to 0, the velocity has to be equal to 0. So, expressed in terms of these wall units, okay, okay, very close to the wall, okay, the equation in the viscous sublayer is just that ux plus is equal to y plus, okay, in the viscous sublayer. Okay. Beyond the viscous sublayer, okay, there is of course the turbulent flow. Okay, there is turbulence here. Okay. However, in between the viscous sublayer and the turbulent flow, there is what is called a logarithmic layer. Okay. And you can derive a velocity profile in this logarithmic layer. Okay. I will not go into the details here because that involves matched asymptotic analysis, but you can derive a velocity profile. In this case, ux by u star is equal to a times log plus b, okay, where a and b are considered to be universal constants. Okay. A is about 2.4, okay, it is close to 2.5. And b is about 5.5, okay, approximately. These constants are determined by actually fitting the velocity profiles to this logarithmic function. Okay. So, expressed in wall units, up to about y plus is equal to 30, we have a viscous sublayer. y plus is equal to 30 to about 200, we have a buffer layer, a logarithmic layer. I should plot it here. And beyond that we have the turbulent flow. Okay. So, that is the structure of the flow in a turbulent flow, the viscous sublayer where u plus is equal to y plus simply because we have scaled it this way, and then a buffer layer where once again the velocity scale is the friction velocity and the length scale is this length scale, okay, the wall unit length scale. Okay. Yeah. So, that is the broad structure of a turbulent flow. Okay. I will come back and I will revise this a little bit in the next lecture because it probably went a little fast, but once we do that then we will look at other kinds of problems. This is just a steady unidirectional flow, we look at more complicated flows as we go along. Okay. But this is important because this kind of a turbulent flow structure is something that is used very often, okay, in description of flows past flat surfaces. We will continue this in the next lecture. Okay. I will see you then.